in this video here, we're going to look at some applications of functions. And so just different applications, and hopefully this will help you do some of the ones that are on the homework. Don't forget, you also have helps on the homework. So up in the upper right corner, if you click on that, those can give you some help as well. So, but I just picked out several. I got 4 different examples here. So this first one, it drew a window here, and the idea of this window is that this is a square. So the bottom is a square, and this top is a semicircle. Okay? And what this wants you to do is find the area of the window as a function of the side of the bottom square. So really what you want here is the area of the window as a function of S. And it's basically the area of the square plus the area of the semicircle, right? So we just have to find expressions for each of those, and then we can find the total area. So let's just do a little bit of review here about the area of a circle, okay, or just the area and the circumference of a circle, both. So if you have a circle with a radius of r, if you remember the circumference, which is the distance around the circle, that is 2 pi times r. So that's the length, the distance around the circle. The area of the circle is just pi r squared. And so that gives you the area of the circle. And then I'll use this, ASC. ASC would be the area of a semicircle, right? SC for semicircle, which is just like 1/2 pi r squared. It's just half of the area of the circle. Okay? So now let's think about this. We want to find this area. The area of the square is easy. You just take S times S, or S squared. Okay? So let's write this. This is just S squared. So what we need to know is the area of the semicircle, okay, which is 1/2 pi r squared. So what is the radius of this semicircle here? Like this distance. Okay, it's the same as this distance, right, around the circle. And this distance, then, the radius, is 1/2 of S, or S over 2. Right? So I can plug that in for R here. And when I do that, I get 1/2 pi S over 2 squared. Okay, well, this would just be 1/2 pi S squared over 4. And then I can commute this 4. This is like 1/4, right? And I can bring it over here, and that would be like 1/8 pi S squared. Or maybe I could even just write it pi over 8 times S squared. Okay? So this is actually the area of the semicircle in terms of S. And this is the area of the square. So what I can do is just plug this back in, plus pi over 8 times S squared. Okay? And so that's my function there. And this is actually right, but let's say you're you actually have a textbook and you look up the answer in the back. And I think there's when you do this online, I think it doesn't matter what form this is. The computer should know that that's the right answer. Okay? But those that's modern technology, right? When I was in college, we didn't have that. And so we would always look in the back of the book, and it would tell us the answer to, like, the odd problems or whatever. And I actually got this from this pre-calc textbook here that I use in my pre-calc classes. And there's the window, and it wants the area of the window as a function of the square, or as the side, a function of the side of the square. And what this has is the area of the window, and this is the answer that it gives. It tells me that it is, actually they have 8 first. 8 plus pi, all this over 8 times s squared. And so when you see that, you might feel, boy, I must have the wrong answer. Maybe I don't know what I'm doing. But you don't have the wrong answer, and so it's always helpful to be able to like get this into the form of what you see in the back of the book. Because that's really good practice with your algebra and stuff. It's a worthwhile thing to do. So let's see if I can get it into that form. So this is what I have, right? And so I can factor out that s, and if I do that, I actually get this. So that's still not quite the same as that. So I think what I'm going to need to do is put this over a common denominator. And if I do that, this is 8 over 8. So I get 8 plus pi over 8, right? And all that times s squared. And it is the same, okay? So if you do problems where you get to see the answer, it's really it's good practice, good algebra practice to try to get things as you have it into the form that the answer key gives. Instead of just thinking, oh, I don't know how to do this problem. Look at that, I'm not even close, or whatever. Just realizing, having confidence in your work, and knowing you just have to show that the two are the same. Because expressions like that can be in many different forms, right? So what I have here on the back is just something that's a little harder. And what this says is, it says find the diagonal of the square on the bottom as a function of the area of the semicircle on the top. So let's call this area ASC, area of the semicircle, and the diagonal of the square is right here, and we'll call that D. And so this is really asking for something weird, isn't it? It's asking for the diameter of the square as a function of the area of the semicircle. And that's a little bizarre. So I plug in the area of the semicircle, I get out the diameter. So how could we do this? Well, let's first write the area of the semicircle here, because we've done some work already, I think, that's going to help us. So if you notice, here's the area of the semicircle in terms of s squared. So it's pi over 8 times s squared, right? So let's go ahead and use that. And we figured that out. So that would be the area of the semicircle in terms of s, okay? And the reason I'm going to do this is that the diameter is related to s, right? And the way it's related is the Pythagorean theorem. So basically s squared plus s squared is equal to the diameter squared, right? And so this would actually be 2s squared is equal to the diameter squared. And so then I could take like the square root of both sides, and I'd get just the diameter here. Notice I'm just taking the positive square root because we're dealing with lengths, and lengths are always positive. But this thing reduces down to the square root of 2 times s. So the diameter in terms of s is equal to this, right? So it looks like if I can solve this for s in terms, so I can get s in terms of the semicircle, and then I could plug it in here, then I would have a function for the diameter. So that's what I'm going to do. Okay, this is equal to pi over 8 times s squared. And so I'm going to move the pi over 8 to this side by multiplying both sides by the reciprocal, and this is just equal to s squared. And then I'm going to take the square root of both sides, and of course I just need the positive one, and so that gets rid of the square over here, and I get s is equal to, and what I can do here is, so this is ASC over pi, right? And so what I can do here is plug this in for s, and I get d is equal to the square root of 2 times all of this, right? Just like that. Okay, now let's say, now this was not in my textbook, I made this one up, but I did do the problem here. Let's see if I can find where I did the problem. I got all this paper on the floor. Where is that? Why am I not finding it? Oh, here it is. Okay. So when I did this problem on with pencil and stuff, let's see, where was my final answer? I have it like scratch work all over the place. Oh, so when I did this problem, I did not get this. The answer I got was d is equal to 4 times the square root of a semicircle over pi. Very different answer, right? So let's see. Let's see if we can get this into that form. And the way that I'm going to do that here is basically just notice that this here is like the square root of 2 times the square root of 8ASC all over the square root of pi. And what I did is I just split the square root up over top and bottom and then brought that up on the top. And the reason I did that is so I could bring that into there. And what I get here is on the top, I get like the square root of 16ASC over the square root of pi. And now the square root of 16 is 4. So I get 4 square root of ASC over the square root of pi. And basically I can put those over the square root now. So when I did it in a slightly different order and got this answer. But I see that I still did the problem right. Okay? And that is what I get. So, some nice problems, okay? And this second one maybe is a little more challenging. So now, let's try a couple. I got 2 more problems here. So this says, find the area of the shaded rectangle here, and that rectangle is inscribed in the unit circle. Okay? And it wants me to find this shaded area as a function of x here. So x is just where the distance from here to here. Okay, because this is just a regular xy coordinate system. And so this is a nice problem. Oftentimes, when you have a real world problem, you might put it on a coordinate. You might put a coordinate system there and choose where your origin is going to be in the problem. It doesn't matter. You know, when you put the coordinate system, you pick it so it's really convenient. Like I wouldn't put it over here, like the origin, and have a circle down here. That would just complicate things. So I'm going to use a unit circle, and then you have this rectangle. Okay, well, I want to find the area of the rectangle as a function of x, right? Well, let me just notice here that the area of any rectangle is just the base times the height. You can write it like that. The base here times the height, right? Well, the base here is actually easy. The base of my rectangle is just 2x. 2x times the height. Okay, now I want this all as a function of x, so I need the height here in terms of x. And notice that, you know, the ordered pair on this unit circle is x, and then this height here is the y value is the height of your rectangle. Okay? And the reason for doing this is a point on the unit circle. So it has to satisfy the formula for a unit circle. And the formula for the unit circle is just x squared plus y squared is equal to 1. And so basically, I want h here in terms of x. So I could say x squared plus h squared is equal to 1. So that means h squared is equal to 1 minus x squared. And then my h here would just be square root of 1 minus x squared. And I'm going to take the positive 1 here. Okay? And so then I could rewrite this here, this whole thing, as 2x times the square root of 1 minus x squared. And that's actually my answer here. Okay? Now, you know, I actually made this one a little more confusing. I should have, instead of doing like the base times height, this could have been, I could have noticed that the height of this rectangle is just the y. So the y here on the, it's a point on the unit circle, and so then I could have just solved this for y and plugged it in. So going through h there, I don't know if that made it a little more confusing, but this wasn't so bad there. So, but this is an interesting problem. So if you inscribe a rectangle here in this semicircle in this way, this is actually the formula of the area of that semicircle. Okay? And so now let's do one more. And this is a lot like the last problem on your homework. And it's a kind of a fun, interesting problem. Now what I have here is actually a little more complicated and thought-provoking than the one in your homework. So if you can do this, you'll do fine on the one on the homework. But basically, this is a race here. Okay, there's a guy named William. He's going to start at the starting line, and he needs to race to the finishing line. And this is actually a river that's 350 feet across. And the race involves both swimming across the river in some way, and then running the rest of the way to the finish line. Okay? Now, the thing is, it doesn't matter if he goes straight across and runs the full 2 miles, because from this point across the river to the finish line is 2 miles. And it doesn't matter if he goes straight across and runs down to the finish line, or, you know, he can go at an angle like this and run to the finish line. He could go straight to the finish line. Now this would actually be the minimum distance. This would be the longest distance, and then these, you know, would have shorter distances. But to go straight from this starting point to the finish line, which would mean he would have to swim the whole way, that would be the minimum distance. But he doesn't want to minimize the distance, he wants to minimize the time. And it turns out that he can swim 264 feet per minute. That's a little, I accidentally said feet per second, but it should be feet per minute. And then he can run 5 miles an hour. And so it turns out he can run faster than he can swim. So the 264 feet per minute is actually 3 miles per hour. Okay? And so he doesn't want to necessarily go straight across and then run the whole way, even though he can run faster, because this here would be a lot longer distance than if he went like here. But he wouldn't necessarily want to go straight to the finish line, because then he's swimming the whole way and he's going a lot slower the whole way. So there's some combination of swimming and running that's going to minimize the distance. This is actually a classic problem for Calc 1 students. And we won't actually be able to solve it using calculus yet. That's going to await a future It'll be in chapter 4 that we do problems like that. They're called optimization problems, where you minimize or maximize the value of a function. But if you remember, when we graph a function, we do have, if we hit second calc, we do have a thing where we can minimize and maximize the value of a function. So as long as I could get the time, what I want to minimize is the time. Minimize the time, right? And I want to find the x value. So where he swims here, we're going to find it as a function of x. So I want to get the time as a function of x, okay? And this is basically just going to be the time it takes to swim plus the time it takes to run. I have t swim plus t run. And so what I want to do is find the time it takes him to swim, depending on where his x is, the time it takes him to swim, the time it takes him to run, right? Now what I'm going to do, I have this in feet. The swim is feet per second, so he can go 264, feet per minute, and he can go 5 miles per hour. And so I either want to convert this to miles per hour or this to feet per minute. And I'm going to change everything to feet per minute, okay? So first of all, there's 5,280 feet per mile. So 2 miles is equal to 2 times 5,280. So it's 10,560 feet. So that's the first thing. This 2 miles is really 10,560 feet. Okay. And then I'm going to switch this to, I need to do 5 miles per hour. Okay. And I need to switch that to feet per minute. Okay. Well, if he can go 5 miles per hour, so I take 5 times 5,280, and what that means is he can go 26,400 feet per hour. So I have to divide that by 60 to find out how many feet he can go per minute. And so it's 440 feet per minute. Right? Okay? So, notice the t of x here is actually going to be the time it takes him to run, or to swim and to run. Now notice, if you remember here, I'm going to write this down here, that rate is equal to, distance is equal to rate times time. Do you remember that? And so if I go 5 miles per hour for 3 hours, then I go 5 times 3, and I go 15 miles, right? So what this means is that the time is actually the distance divided by the rate. Okay? So this thing, it's going to be, I'll say time swimming plus time running. And then the time here is just going to be the distance that you swim, so the time is the distance over the rate, divided by 264, plus the distance that you run, divided by 440. And so what I need now is I just need an expression for the distance that I swim and the distance that I run. Okay, and that's going to depend on x, right? Because I want this as a function of x. So notice wherever I get out, the distance I run here is going to be the remainder after x. So it's going to really be this top number is going to equal, and I'm going to put a thing here over 264. But the distance that I run is really 10,560 minus x, right? And that's over 440. So what about the distance that I swim? Well, the distance you swim is the hypotenuse of this right triangle. So we're just going to use the Pythagorean theorem, right? I get x squared plus 350 squared is equal to the distance that I swim squared. So the distance that I swim is just the square root of x squared plus 350 squared, right? And then that's what I'm going to put up here. And basically now this is my function. And that's the huge part of all this. Okay? And you know, I should have had this already in here before I started the video, but I didn't. So what I'm going to do here is I'm going to plug all this in. So the first thing then is this. I'm going to do the square root of x squared plus 350 squared, and all of that is divided by 264. And now I'm going to add, and in parentheses I'll do 10,560 minus x, right? And then in the parentheses, and then I'm going to divide that by 440. So huge function. And so the standard window isn't necessarily going to give you very much. We can look at the standard window. So yeah, if I do the standard window, and it's thinking, that thing is spinning there. And you can see that this isn't giving me anything. Of course, these are much bigger numbers. So you have to go searching for it. But the easy thing to do is they do have something called Z-Fit. Where is it? I hope they have it. They used to have it. Oh, there it is. Zoom Fit. So, and that's that one right there. And I'm going to hit enter, and it's going to pick a window. Now, it doesn't always pick the best window, necessarily. But oftentimes, it can give you a good start. Okay, that's not necessarily the best window. So what I'm going to do is I'm going to zoom out now. Yeah, I'll just go like that. And that still isn't that great. So maybe I'll zoom out again. And you do see that it's curving around now. So that's nice. And so I think what I need to do here, and of course only positive values matter, I'm going to now change my window. So this is what I get here. And so what I'm going to do here is I can start this at, well, yeah, I can start it at 0, but let me take this here to something bigger than 160. So I'll take it to 500. Okay, and then you can see my Y min and Y max are very close together. So that's surprising. So let's keep that. So now it's starting at that, and you see it's going down. And it does curve back up, very surprisingly. And there's a minimum value in there. And that's actually the answer to my question. So it takes some skill to find these things. Because this window, it's like 24.5 to like 25.5. The Y window. to capture this, right? And this is like 0 to 500. Okay, so you have to play around with this, and you can use Z-fit maybe to start. Zoom out until you kind of see what's going on, and then maybe go in and adjust your window. Okay, there's all kinds of things that you can do. So now what I'm going to do is I'm going to go to Second, Trace, which is my Calc menu, and I'm going to go to minimum. I want to find a minimum value. Okay, and here it's not quite as clear where it is, so I'm going to make sure I'm on the other side and hit enter, and then make sure I go all the way to the other side. Make sure I'm on the upside, right? And there we go. And then I'll just go kind of to where that minimum value might be. And it gives me x equals 262.5 feet. And the minimum time, the t of 262.5, and let me zoom out here now. The t for this is like 25.06. Okay, minutes for the race. Okay, so what this means is the best time that he can get is going to be when he swims across, so that he is 262.5 feet from the point directly across. Okay, and so what we're learning to do is doing this function. And then you can use your calculator actually to find minimums, but it's going to actually learn how to do this by hand. It takes calculus, and it's going to be near the end of the course that we actually learn how to find this minimum x value that minimizes the time. Okay, so this is a great problem. This is a classic problem in Calc freshman Calc 1 text. And you probably see something like it at some later point. But this is just getting you exposed to that. So there you go. There's some applications here. And this finishes up this first section on functions. And so good luck on that homework. If you have questions, please let me know.